Hi everyone, this is part 2 to the amplifier build. If you haven't seen part 1, it's the video just before this one. In this video, we're going to take a look at how many watts this little amplifier makes factory, so that's with this little IC right here. It says it makes 15 watts. I don't know whether that's 15 clean watts or 15 absolutely distorted and square waving watts, but we'll find all of that out. We'll take a look at some data sheets on the ICs and I'll show you what to look for. We're going to take a look around in here for signals. We're going to compare the input signal to the output signal to see how much headroom we have for the next amplifier that we're going to add in this. So basically a phase inverter and an output stage. That's something that's very important. Do we have to add another stage of amplification to get the signal up large enough for the phase inverter and all that kind of stuff? Or do we have enough right at the input pin here? All of this stuff is yet to be discovered. So there's a lot of really interesting things happening in this video, and I'm excited to get started with this. So I'll go grab some data sheets and let's get going. This is the data sheet for the audio output IC. And if we turn this audio output IC this way, it very closely matches the pin configuration. So you can see we have pins 1 through 5. So pin number 1 is the non-inverting input, and that would be this pin right here. It just basically goes 1, 2, 3, 4, and 5. The second pin would be the inverting input, so our signal is going to go into pin number 1. Pin number 3, it says negative VS, so this is going to be our negative supply output pin, and then our positive supply. So we have a negative and a positive rail in this. Now, whenever you come across anything like this, it's very common for the manufacturer of the PC board or the guy that's designing this to copy this closely. Now, there might be some variation in this to adapt this into their design, but it's usually going to be somewhat close to this because this is tried and tested, and they, the manufacturer of the device itself has spent a lot of time with this to make sure that it's nice and stable. So we'll take a look a little closer at the design here and see how closely this follows what they've done on here in just a little bit. So what we want to do with this is we want to see what they're telling us, and nothing is really on this page that's going to give us too much information that we can't find on the second page. The second page is where all the good stuff is, and a lot of repeats to what's on the front page here. So if we take a look at the output power here, we can see that for a voltage positive, negative 19 volts, this is what we're going to typically get right here. So you can see resistance load, 4 ohms, 18 watts. So the minimum is about 15, so there's some variation in there. So our max that we're going to see is about 18 watts. And if we look here, it says distortion and frequency 40 to 15,000 cycles. So that's pretty good. So whether this little transformer is going to give us that, I highly doubt it, but we'll find out here. We'll see how many clean watts we can get out of this little IC on this heatsink right here. The heatsink is, a little sketchy for that kind of power too, so we'll find out at any rate. So now you'll notice here it says supply voltage, and it says maximum positive negative 22 volts. Now, when you're dealing with vacuum tubes and things like that, a little bit of over voltage in many situations is absolutely fine because vacuum tubes are pretty much, well, I wouldn't say indestructible, but they're very, very tough devices. These things, if you were to operate this at positive and negative 22 volts, you would be playing on the edge. So it's always a good idea to run the device just a little bit lower. And as you can see here, as they're saying, 19 volts, I'm kind of telling you, it's getting, that's any more than that, you're kind of pushing your luck. And if you've done any experimentation with any of these modern ICs, op amps, things like that, you'll find that if you have an op amp rated at 18 volts and you're running it at 18 volts, the thing's going to get hot. And not only that, if you have any line excursions or anything that'll bring it beyond that, chances are you're going to destroy that IC. So it's always good to run a few volts lower. Now, with a small transformer like this, and its, current delivering ability, we have two large filter cans here that as soon as you apply the power to this device, this has got to go, get rectified through a bunch of diodes down here, and it has to charge these two devices. So when you turn it on, getting spikes really isn't too big of an issue. So say this thing is going to be running at, 20 volts or 19 volts or whatever they've got in here. Say it's going to be running at that. When you turn the thing on, it's going to come up, but it's not going to spike and then come back down with something of this size, because again, it has to charge these things up as well as power the circuitry here. So in a way, having large filter cans, and sometimes even just a little bit larger than factory, when you turn the thing on, they come up nice and slow and you don't get a spike. You don't want any spikes that go beyond positive, negative 22 volts, or, this thing here is going to eject parts of its, part of its body here. We don't want anything like that happening. So these things, they split and they shoot chunks of the epoxy off and do all sorts of bad things. So they are a really nice IC, and since this is an obsolete product, so I find this really interesting. I get these sheets all the time from, the suppliers that I order from, especially if I'm designing something, and it will say, end of life kind of thing. So it's the end of the life for the device. And, you have such a good product. This thing has been in use for so many years, and it's a stable device, and it's in so many different devices, but now it's made obsolete. It's a really bizarre thing. There are a lot of through-hole ICs out there like this, with many more pins on it than 5 pins. But I guess maybe they're just not getting the sales that they need now, or maybe everybody's just putting stuff on a surface mount platform and they're using, heavy traces as heat sinking, maybe carrying the heat through, things like that. I don't know what they're doing, but this is such a solid product. It's really sad to see this thing go obsolete. And it's the same thing with those XR ICs that I have. The power supply in the Curve Tracer uses an XR IC, and those things they're obsolete, and they are such great, ICs. XR made great ICs. They made an entire function generator in one teeny little IC. They did so many great things. But, again, it's good. So, hey, if it's good, let's make it obsolete. Anyways, that's how it goes in this industry. I have boxes and boxes and boxes of perfectly good ICs. I can't even tell you how many ICs I have. And, they're surface mount still. They work perfect. But again, they're an end-of-life thing, so it's unfortunate. It really is. So whenever I'm working on projects with all of you, I'm trying to make sure now that everything is still current, everything is, still going to be in production so that they're easy to get for everybody here. So, the end-of-life things are, if it's some really specific application that I'm building and something's still available, online, and they are, say, a good offshore supplier or something like that, in some cases I will do that, but I try to keep everything as current as possible here. And of course, this is just going to end up getting removed from this thing anyways, so I'm not really too concerned about that IC. I'll just take this thing out and put it in my parts bin, because these are great. They're great to make audio amplifiers with and things like that. And again, same with the 2050. The 2050 is a very nice IC as well. Down the road, we're going to design a complete audio amplifier, maybe 50, 100 watt audio amplifier per channel. We're going to do that as well. So there's a lot of really neat things coming. We'll use ICs, and if I design a vacuum tube audio amplifier that makes 100 watts and everybody wants the parts to be current, that will be very pricey though. Like transformers to put a 100 watt audio amplifier together are very big and heavy, and I think around the 250 Canadian, $275 Canadian mark or something like that for one block of iron for one channel. And then you need one for the other channel, and then you need a power supply. So that's the only problem with going with some very, very large, power, right? Large power is large dollars. But you can let me know in the comments below if you want me to custom design a huge amplifier, 100 watts. I can get 250 watt audio transformers too. I can get some pretty big iron happening. It's just, all what you guys are into as well. Those building amplifiers, 250 watt amplifiers, is pretty interesting when you're dealing with in the testing stage, because if you have a test speaker hooked up to it and you come across one wrong pin or something like that, say you just even touch the input pin, your test speaker is annihilated. So yeah, it's kind of interesting when you start dealing with power levels like that. I don't know if I've ever shown you, I have a 2000 watt audio transformer. So one day maybe I'll get my forklift and bring this thing in here and we can take a look. So it has spark gaps on the plate side. So anyways, I'll fill you in on that in another episode. If you're interested in seeing that that very large audio transformer, you can let me know in the comments below as well. Anyways, back to this thing. So we know that this thing here says it's supposed to be putting out 15 watts. Whether it's going to put out that 15 watts, it claims here on the data sheet again that, you know, we can get 18, you know, at say 19 volts. Now, whether this thing, you know, it may supply that, but under load is going to be something else, because as you can see, you know, like, I mean, there's a teeny little audio transformer or a power transformer here. So there's a good chance that that isn't going to happen. But you know what? I'm going to get a load. So what I'm going to do is I'm going to get a 4 ohm load for this, because this is hooked up to a 4 ohm speaker. So we want to see exactly what's going on. I'll put a 4 ohm load across this, and then I'll just grab my scope. It'll display watts at the same time, and we can look at the sine wave. And when that sine wave starts to clip or starts to go square, that is the maximum amount of power before it starts going into distortion. So I always back down the gain a little bit until we have a nice sine wave just before it starts to go flat. And we'll see how many watts this thing makes clean and how many watts this makes dirty. So this should be very interesting. This is always the exciting part, to see, you know, how well this holds up to, you know, what it says on here at any rate. So I'll get that all set up and I will be right back. The moment of truth has arrived for this little amplifier. So how many watts do you think this will make clean? And how many watts do you think this little amplifier will make dirty? If you want, you can pause the video and write it down and see how close you come to what this is actually going to do. So I have this attached to a 4 ohm load. All right, so the 4 ohm resistor is right across over here. And I also have the oscilloscope attached to that as well. So we can directly read the watts here. This will do the math. And we can also watch the sine wave to see when it starts to clip or when it starts to distort. So we can see how long it stays clean. And we can also take a look at the distortion. Now I have everything maximized here, so I'm being nice to this amplifier, okay? I have everything maximized to keep that signal clean as long as possible before it'll run into distortion. So I'm trying to be as nice to this little thing as possible. So the drive control is pointing at 9 o'clock right now. You can see this little button here is pushed in, okay? Volume, master volume, max, treble at minimum, middle at maximum, bass at maximum, and we need the reverb at minimum to keep that distortion down as well. And that's how everything's set up. So here we go. Let's find out. So I'll start turning up the signal generator right now. So we're at 1 watt. The exact frequency isn't all that incredibly important, as long as it's around 400 cycles or something like that. Again, I'm trying to be nice to this thing. 5 watts, 5.2 right there. Nice clean sine wave. 7 watts, no problems there. 9 watts. Oh, it's starting to go flat on the top at about 10 watts. So I'll back it down until that is a nice clean sine wave. And I would say 9 watts, maybe high 8s, 9, something like that, just before it starts to show signs of distortion. So I'd say 8.7 is nice and safe. So that's clean. All right, so now when I start bringing this up, look at how this looks into distortion. And it's making just about 14 watts. And it's a very nice looking square wave generator at that point. Now, in the end, when we crank up the tube one, we'll see how it distorts. You can see, like, that's what the distortion looks. It's really hard in this thing here because it's a solid state device here. Now, I got to be careful when I do this because this gets hot extremely fast. And that little heatsink is cooking right now. Let's see if I can show this on my little flare here, if I can get that into focus. Just move the focus over here, so pardon the jiggling of the camera. You can see that in there. That's getting pretty toasty. That's getting pretty toasty down in there. And consequently, so is this little regulator right down here. I'll put my finger on top of it. That little 5-volt regulator right there is very hot. So hot that I can't really keep my finger on it without it getting uncomfortable. So, and we have some diodes down here that are getting toasty, probably Zener diodes or something like that. So you can see that's very hot. Now I can't get a, the sink is reflective. You can see it's nice and shiny here, so it's hard to see that. But you can see the IC at any rate. The black on the IC is it's very hot right there. So I'll just shut this off. So keep in mind, whenever you're doing testing like this and you're bringing things into square wave and you're bringing this thing up to its maximum, that the sink is going to get hot. It's already cooling down, but it's going to get hot very, very fast. So keep in mind that depending on the design, doing this with a design can sometimes be a destructive test. Always keep that in mind. So if it's a destructive test, there's a good chance sometimes you could destroy the audio output. So that's what's going on. We can see that, again, about 9 watts or so before it starts. You can see it just starts to, about, I'd say safely 8.7 or 9 watts. Nice and clean, and then it just goes into really hard distortion at about 14 watts. Now I might be able to, let's see if I can add some other controls here, and no, it's gonna cap out. So it's very close to what it says. Maybe with a different IC, or maybe if my line voltage was a little bit higher, it would probably touch 15. So it's not bad. It's doing it in full distortion, mind you. It's not clean, but it's pretty close. Now, here's something very interesting. So why is this rated for, say, 15, 18 watts, something like that? And why, if this is doing what it's supposed to do, why is it distorting so early? Well, you have to keep in mind that this transformer, it has to feed this thing, and this thing is going to try and drive a load. It's basically driving, you could call 4 ohms almost a short. So, this thing has to drive a 4 ohm load. So it's taking the current that this thing is supplying and feeding it into 4 ohms. So what's going to happen when we give it lots of amplitude? Well, what do you think is going to happen to the voltage on this when it's not regulated? Well, if it has to supply current, the voltage is going to take a dive, right? And what we'll do is I will grab, since this is not regulated, this will probably show that very nicely. So I'll grab a voltmeter. I'll just leave everything hooked up the way it is. And we'll take a look at the supply lines here, and we'll see how much this actually does dive down. We'll see where the voltage is. So it says 14 times 2, and then of course that's rectified and filtered and everything like that. So it'd be interesting to see where that's actually sitting. So I'll get that all set up and I'll be right back. I'm about to start probing around in this amplifier with the AC supplied to it. So I need to warn you, if you're following along, you're doing so at your own risk. Know that there is exposed AC line in this, and that does pose a shock hazard. So if you're uncomfortable with doing this procedure, definitely do not do it. Now, when I'm probing around, even on the low voltage side here, I got to make sure that I have very sharp probe leads so that when I poke the probe leads into the solder, there's no chance of me slipping. That's why it's so important to have very, very sharp leads. Now, of course, there's been many times I've grabbed them and I've actually cut myself with these things. They're so incredibly sharp. But I have to tell you, if you slip and touch these together, even with this low voltage, which isn't all that incredibly low on the secondary side, and then these charged capacitors on top of it, you're going to be melting your leads, blowing traces off, and possibly causing damage to the power supply board and maybe even yourself. So there are lots of risks when working on something like this with the power applied to it. So again, if you're uncomfortable, do not do these procedures, and if you're following along, you're doing so at your own risk. What I'm about to share with you here, or demonstrate to you, is very important to remember, and you can look upon this like one of those little golden nuggets in understanding. Not only is this relevant to this small amplifier, but it's relevant to large amplifiers, small and large power supplies, vacuum tube audio amplifiers, and many different electronic devices. You'll see what I mean here in just a few moments. So what we're going to do is we're going to take a look at the voltage when this is idling. So we're going to take a look from rail to rail. We'll take a look at the voltage when this is not feeding any current into the load. So I have my signal generator turned down. Then what I'm going to do is turn my signal generator up. So what it's going to do is it's going to tell this thing to start feeding 400 cycles into that 4 ohm load, and we're going to watch what happens to the voltage in the power supply. And then I'll explain a little bit about vacuum tubes and why a lot of the guitar amplifiers and even audio amplifiers are built with vacuum tube rectification instead of solid state rectification. Again, it's all about sound, right? So I'll turn this on, and I'm going to go right from rail to rail. So if I go from this rail here to this rail here, we're going to have 40 volts. So if I go from basically ground to one rail, it'll be 20 volts. So 20 volts positive, 20 volts negative. I'll show you that here in just a little bit. So this is what it's at when it's idling. So it's right at 20 volts. So they're keeping that 2 volt safety region there. So I'm going to start turning up my signal generator here. Reach over to it. And look what happens at just 1.2 watts. Look what the voltage did from 40 down to 34. 4.5 down to 29. 8.7, it's at 27. So it's gone from 40 volts down to 27. So if I shut it off again, right back up to 40 volts. Or close to. So I'll turn this back up again. Okay, so we'll bring this into distortion. Down to 25, from 40 down to 25 now. So I'll just bring this right heavy into distortion, right down to 23 volts. That's at about 14.4 watts right now. So my line voltage probably went up just a little bit. It is late in the evening here. So from 40 volts down to 23.5 pretty much. So what's happening? So I'll just remove these here carefully. So what's happening here is when I'm turning up the signal generator, what's happening is this thing here has to feed 400 cycles into that 4 ohm load. Of course, 4 ohms is, I often joke is a dead short, but it's, pretty close to it. So this thing has to feed a 4 ohm load, and it's using the current supplied by this transformer. So as this thing is delivering current to the load, of course, it's sagging down. And as you can see, it's sagging down a lot. Now, if we look at that was 23.5 volts or something like that. So now I'll show you what I mean here from just the ground. So we have a positive and a negative supply here. Okay, so go to the positive supply. We should have close to 20 volts. There we go, 19.7. Okay, so that's positive 19 volts. And then if I go to the next pin, we're going to have negative 19 volts, negative 20, close enough. Okay. So now, of course, if we go from end to end, that's right from the negative right to the positive, we see the full amount there, right? 39.8. So basically 40 volts right there. So now if I leave this in here, I don't know if it's going to make connection. This is too sharp. Might need to use a different probe. There we go. So there's negative 20 volts. It popped out. Let's put this one back in here. See if it'll stay. I don't think so. So what I'm going to do is I'll go over to the other pin here. I'll force down on that one and force down on this one. Okay, and I'll turn this up and now watch what happens. So that's going down to 11.7 volts. So from 19.6 down to 11.7. So if we take this to the point of where it's right till it's, starting to distort, 8.9 watts, we're at 13 volts already. So it's already gone all the way from almost 20 volts, right, down to 13 volts. Give it just a bit more amplitude, bring it up to 9 watts there, amplitude there. It's 12.7. Look at how that power supply is just caving. right? And this happens in a lot of different devices. In large linear power supplies, you have big transformers and a row of pass transistors. And what's happening is the voltage is really high at the collector of the pass transistors. So it'll be about maybe 30 volts or something like that. And then at the output pins, it's usually 13.8 in a regulated, 12 or 13.8 volt power supply like an Astron or something like that. So what's happening is those transistors are acting like switches. So as you draw load from the power supply, so say you have 13.8 volts, and say you're going to feed a something that's going to draw 30 amps. All right, so whatever that is. So say you're feeding a radio that's going to draw 30 amps under load or something like that. Okay, so when you draw 30 amps, you'll notice the power supply, it stays at 13.8 volts, right? Because it's a regulated power supply. Well, what's happening is that transformer that's maybe supplying 30, 32 volts, something like that, when you draw a load like that, it might be going down to, say, 20 volts, maybe 22 volts at 30 amps. But you know that it's still at, say 20 or 22 volts, it's still much higher than the 13.8. So it's still up here. So since it's drawing current, it's dragging the voltage down as well. And then when, of course, you remove the load, it pops back up to, say, 30 volts or something like that again. But since it's regulated, it's always keeping this at 13.8. And that's what those pass transistors are doing in there. In a case like this, there is no regulation in here. This is just, a power supply that's running this thing. It's just windings into diodes and into this is what I should say. So when we look on the data sheet here, we can see that the optimum results were at 19 volts, right? To get what we're saying here, or we're seeing over here, positive and negative 19 volts. So that's pretty much where we're starting off at. As soon as we give this just a little bit of volume, the current is just making this transformer is tanking. It's going down, right? That's because it's small. Now, there's a bunch of things that need to be understood about this in a guitar amplifier. Now, if you were looking at this in a hi-fi amplifier and you saw that happening and say it was supposed to deliver what it's supposed to do clean, you would look at that power supply as being a cheap piece of junk, right? Because it's caving. It's going right down. As soon as you start to draw any current from it, the thing is just, it's getting pulled right down. So in a case like this, where it's a guitar amplifier, they're looking for this thing to distort. They want this thing to distort when you're playing guitar. If you're playing, say you want that grunge sound or whatever, they want the thing to basically be soft. So in a case like this, it really is kind of a balance point in the design here. Again, hi-fi, you don't want that. You want big power supplies, something that's regulated. So the power supply is going to stay, like, as I mentioned, like that Astron power supply where it would be at maybe 32 volts and then supply 13.8. And then if you were to pull, say, from 0 to 32 amps, it's just going to stay at 13.8 because there's pass elements in a control IC, usually an LM723 or something like that, controlling those and telling those transistors, okay, turn on and supply more current and then quickly shut off when you remove the load. So they're acting like big variable resistors that move incredibly fast, right? They're turning on and supplying current, and then when you remove the load, it immediately shuts down again so that it's regulating the voltage, right? Now, in this case, again, it's sometimes desirable because you want that distortion. Now, in a vacuum tube amplifier, here's where it gets even more interesting, is vacuum tube rectifiers have a lot of drop across them. So even if you have a large power transformer that is going to supply a lot of current, vacuum tube rectifiers are very soft. They don't have 0.6 of a volt drop across them or something like that. Some of them have 10, 20, 30 volts drop across them, depending on the rectifier and how big the rectifier is. And the drop is usually rated in the data sheet. You can see the drop, say for a 5Y3 or 5U4, 5R4, things like that. So if you're going to start to use rectifiers that are indirectly heated, not directly heated, indirectly heated, tolerances inside are a lot closer and there is quite a bit less drop in them. It depends on the manufacturer who's designing it. So you can put a really stout transformer in a vacuum tube amplifier and then put some soft rectifiers in it and get the same kind of effect. So it's really kind of interesting. It's a cut in the design. And as we're designing different amplifiers together, I'll give you lots of examples of this and you'll see exactly what I'm talking about. So again, this doesn't only apply to this. This applies to power supplies. Power supplies are doing this too. Like, as I say, your Astron is doing this. That power supply transformer is tanking when you draw load. It's just that they're keeping that level far enough above what you need that you don't see the difference at the output pins. So for example, if you had a small transformer and it was supplying 13.8 volts and say it was up at say 25 volts or something like that, and you drew maybe 30 amps, it would pull it right down to 13.8 and below, and the power supply wouldn't be able to supply it anymore because of the drop in the transformer. And that's why the transformers get bigger and bigger and bigger, so that they can supply more current, so they can basically hold their own under load. So some very important things to remember here. And as you can see in this amp, that thing is really caving. That's really going down. So space considerations, maybe they designed it like this because they wanted the distortion. It's, really the way it is. So as you saw, it's, 15 watts maybe into full distortion, maybe 9 watts clean, something like that. That's the design. So when we start going into this thing and putting the the vacuum tubes in here and things like that, we'll take a look at the difference between that. Now, this is such a small amplifier that the chassis space on the other side is really limited to put a big power transformer, and we have to put a power transformer on this thing, and then on this side we're gonna have to put an audio transformer, and then we have to have 2 tubes on here, so we're running out of chassis space mighty quick here. If I wanted to put a vacuum tube rectifier in here to make things nice and soft, to get that really kind of that soft coming into the distortion, really soft, things like that, I might actually have to put another separate power supply in the bottom of the cabinet. So I believe it was Fender did that in some of their designs. They would have a separate power supply, and they had a cable running up to the top. It looked like BX cable, and the wires were shielded in that. So that could be an option as well if we wanted to do that. Let me know your thoughts on that. Do you think we should kind of go all out, put vacuum tube rectification in here, or should we stick with solid state rectification and keep the transformers on this one platform so that it's all contained on this? What do you think? So there's lots and lots of options yet. So in the next video, we're going to choose an audio transformer using the data sheet for the 6360 vacuum tube and things like that. So there's a lot of really interesting stuff coming up here as well. We'll have to, get an audio transformer, fit it, and do all sorts of interesting things, put tube socket holes in the chassis and all sorts of good stuff. So at any rate, so we know that the power supply in this thing is really, it's tanking. But what we're going to do now is we're going to take a look at the output signal. So I'll reconfigure the scope here. We'll take a look at the output signal, and now we're going to take a look at the input signal to this IC. And we're going to see how much headroom we have left to drive a vacuum tube circuit. So I'll give you an example of that here in just a moment. Let's take a look at the input signal versus the output signal, and I'll explain a little bit more about that here in just a moment. So I have channel 1 here, or A I should say, attached to the 4 ohm load, and B is my probe here, and I'm going to look at the input pin to this IC. So you can see that this is at 100 millivolts per division, and this is at 5 volts per division. The reason this is so high is because it's at the output, it's monitoring the output here. So we're looking at peak to peak. Now, what I'll do is I'll put this on the input pin of the IC. So this is where the signal comes out of all of the rest of the preamplification circuitry and ends up going to the input of this IC, which is pin 1. So what I'll do is I'll turn up the amplitude here. I'll use the drive control on the amp. So for 12.5 volts peak to peak right now on the output, it's taking 0.23 volts peak to peak drive, and that's the purpley blue looking trace right here. Okay. So now what I want to see is I can see that, see how this is already into distortion here? So we're at about 17.5 volts peak to peak. You can see how that's heavily into distortion already. So we're probably at our, 10 to 12 watts somewhere, just starting in there, right? Just before that, it was nice and clean, right about here. So we would be just in that, before the distortion wattage right now, 16 volts peak to peak. So now you can see that I've only got 0.35 of a volt at this point to drive the phase inverter and output circuit from. Now I'm wondering, let's turn this down so I don't overheat this little section here. So I'm wondering, when I drive this thing into distortion, right, as you see here, we can see that this is distorting. Is the input signal to the IC distorting as well? Is the distortion here, or is all the distortion being created in the output section? Okay, so as you can see, look at all that distortion at the output, but the drive signal is still nice and clean. So we're achieving our distortion in this little IC right here, right now, which gives us a little bit more headroom. Okay, so if I turn this way up, so look at how that's full square wave, and we still have a nice clean sine there. You see that? Went right off the screen. So we have a lot of drive there. Now, depending on the phase inverter circuit that I'm using, and the topology at that time, will decide all that when we use the 6360 and the audio output transformer. We'll see how much chassis space we have left and what kind of tube would be the best for that. Again, we'll go through every step together here. So we'll see if we have enough drive. If there isn't enough drive here, there's a chance that we may be able to modify the circuitry to give just a bit more drive, or we might be able to add one small little amplifier in line before it goes to the phase inverter. Now, it's all solid state up to this point, so we could add one more small solid state amp before the phase inverter, and then the phase inverter and the output would be vacuum tube. So some of you might be saying, well, why not just leave this thing in here and use it for the drive? Well, the drive that's coming out of this thing is pretty extreme. So that's way over the top, 13 volts peak to peak. That's a crazy amount of drive there. So again, all about the balance. So if I say advance this to say 200 millivolts, let's go to 500 millivolts per division, okay? So you can see there's a lot of signal there, even into hardcore distortion. Now you can see that this is starting to distort. So if we back this off to say 200 millivolts per division, you can see that this is going to start to distort. You can see it's looking kind of interesting right about there, about 1 volt even. So you could say that it still looks like a decent looking sine wave, even just before 1 volt. It's a lot nicer than what we're seeing come out of this thing. Nice and warm now. Yes, you are, little IC. You're getting nice and warm. So, again, we might be able to modify the gains in this actual unit, or if not, looking at the actual circuitry design, one small amplifier before the phase inverter would do it. Even one transistor would give us enough. So that's where we're at. So they're achieving their distortion in the output stage. So we've discovered that right now, and we've also discovered that we have a lot more drive to go after, this thing starts falling into distortion. It's still nice and clean there. The drive signal is not looking bad whatsoever. See if I play with the any of the other controls. It stays not bad, It's not too bad at all. So all in all, this is starting to look really, really promising. That is cooking hot. So in the next video, what we're going to do is start designing the vacuum tube stage. Now, what we're going to do before we start building anything into the platform here is we want to build the actual amp external to this, just in case. Say we design something around a transformer and a vacuum tube, and say something doesn't work out when we have the thing all drilled and the transformers designed. At that point, you're past the point of no return. So we will build everything outside of the amplifier and run basically umbilical cords over to this, from the amplifier to the vacuum tube amplifier, make sure everything is good. Then we're going to start working on fitting it in here, and then we have to fit a power supply into this as well. We need to make sure that there is minimal to no magnetic coupling between the power transformer and the audio transformer, not like this, like this. So we need to keep that out of there. We also need to keep a lot of things into consideration, like where we're going to put the preamplifier tube. It might be beneficial to mount the audio output transformer here, mount the audio output tube closer to the power transformer, and then mount the preamp tube closer to the audio output transformer to get that preamplifier, or I should say the phase inverter tube, away from the power transformer so we don't get any coupling, magnetic coupling, any hum happening. So there is a lot of things that we're going to have to experiment with, and a lot of that will actually be laying components on this chassis, just putting them on and turning things physically around like we did in the 6-pack amplifier video, looking for minimal hum and things like that. And that is all absolutely needed in any type of new design. You can't just drill holes and put transformers in and expect something to work, because it may look good aesthetically, but electrically it looks pretty ugly. You know, that's the way it works. So it's all about that balance. You need it to look great aesthetically, and you need it to work great electrically. Let's follow the audio signal path from this dual op amp right here to the audio output power amplifier. There's 2 op amps in this small package here. The output to one of the op amps goes to pin number 1, and the output from the other op amp goes to pin number 7. So pin number 1 is by the dimple here. Pin 1, 2, 3, 4, pin 5, pin 6, pin 7. You can see pin 7 joins these 3 components here with this trace through this 1K ohm resistor. You see this large trace here, through the capacitor, up this trace, through this 10K ohm resistor, through this trace up here, through this capacitor, which jumps this trace right here into pin number 1 of this audio IC, which is the input to the audio IC, as can be seen right here. 22K ohm resistor to ground on the manufacturer's data sheet, 22K ohm resistor to ground in the design. So you can see that the manufacturer of this device, or of this circuit board, followed the data sheet very well. 22 microfarad capacitor, 470 ohm resistor right here, 22 microfarad capacitor here, 680 ohm resistor here. So they've modified this network just a little bit, which is to be expected. This capacitor here isn't on the data sheet, so this is added across this 22 microfarad capacitor, either to tone things down, to stop this thing from breaking into oscillation, or it might just be some form of a decoupling capacitor in here. Again, it looks like an RF engineer designed this thing. Guitar amplifiers are very susceptible to picking up stray RF from ham radios, CB radios, and even cell phones. That long cord that runs up to the guitar a lot of the times acts as an antenna, and if there's any transmissions very close to the thing, a lot of the times these things will broadcast that transmission very loud through the speaker. So putting decoupling capacitors in here is always a very good idea. Now, there's always a balance point with decoupling capacitors, because depending on the value of the decoupling capacitor and where that decoupling capacitor is put will also affect the tone of the amplifier. So I'll get into that in the future here as we're designing this and as we're designing other amplifiers. It's a very important thing to understand. There's always a balance point. You gain something here, but you lose something here. That's the way it is with everything. And electronics is definitely no exception to that. So I hope you've enjoyed. We're now on to part number 3, where we're going to start designing the output section, work our way back to the phase inverter and power supply. Lots of very, very interesting stuff coming. If you enjoyed this video, you can let me know by tapping the heart symbol below, and I'll talk to all of you very soon. Bye for now.